We proposed a new computational framework that recasts three-dimensional cloth deformation as an RGB image in a two-dimensional pattern space. Using UV space of the cloth mesh as the domain, each vertex stores a vector-valued function of displacements dx, representing perturbations in the texture coordinate and normal directions. This vector-valued function at each UV vertex can be conveniently interpreted as an RGB color. Thus, we refer to these vertices as cloth pixels. The cloth pixels can be interpolated to a background Cartesian grid of pixels to generate a cloth image. We generate real-world positions for the cloth pixels by barycentrically embedding each of them into a triangle of the body mesh in the rest pose. As the body moves and deforms, the cloth pixels move along with the triangles they were embedded into. And applying the dx offsets to the real-world locations of the cloth pixels yield the 3D cloth shapes. The process can be reversed where we record the cloth shape as dx displacements and store the RGB values on the cloth pixels embedded in the body mesh, which in turn correspond to a cloth image in the pattern space. We demonstrate the efficacy of our approach on the synthetic t-shirt dataset. We sample random body poses and simulate the t-shirts using a physics engine. Some examples are shown here. We train a CNN to predict cloth image given input body pose parameters. The predicted cloth images are interpolated back to the cloth pixels in the texture space. The cloth pixels are skinned onto the posed body using pre-computed weights. The displacements encoded in these cloth pixels are then added to their skinned locations to obtain the 3D cloth shape. To train the network, we use two loss terms, an L2 loss defined on the cloth images, and a cosine loss defined on the per vertex normals. Here are some examples from our best loss model. To better learn the cloth images at higher resolution, we use a support cage to divide the cloth mesh into smaller, semantically coherent patches. This allows the network to enjoy a higher level of specialization and performance. And indeed, the models trained on patches can better capture folds and wrinkles. Finally, for generality, we also show a necktie example. Even though neckties are loose and can drift far away from the body, the model is able to make decent predictions.